Hello everyone, welcome back to my channel. Today let's go over a medium question that I finally solved on my own after a lot of trial and error. So I'm really happy about this and let's go over it. So basically you are given a zero indexed array. So the question is called minimum absolute difference between elements with constraint. Basically the idea is you have elements that are at least x distance apart and you want to find the minimum absolute difference between any of them. For example, if you have this, then you're going to say when you're at index 0, you're going to be comparing 2 and 4 because from the current, these are at least 2 away from this, not 2 away from each other, right? When you're at 3, the only option is 4 because that's the only element that's at least 2 places away from the current element of 3. When you're at this one, then you're going to have this as the only option because based on the current element, this is the only one that's at least 2 places away, right? So the n squared way of solving this, which I tried before, is pretty trivial. So for I in range length nums, for j in range I plus x length of nums, right, at least x places away. You want to find the minimum absolute difference. So result equals minimum of result and absolute nums of I minus nums of j, and then return result at the end. So technically this works, but it's obviously too slow. It's an n squared. This one has a very low acceptance rate and you got to be more clever. So it took me quite a while and I'll show you what I did. So 34.8% is not going to cut it. So you're almost there, but you're not there. So let's keep the result because you know you're still going to return that at the end. We're going to return an integer. And so the idea is that we're going to segregate, right? So we're going to go from left to right for I in range length nums. So we're going to take our current element and we're going to see whatever is to the right side and to the left side, if there is a left side, right? So when you're at 4, when you're at index 0, there is no left side. There's only a right side because 0 minus 2 is less than or equal to 0, right? And then from here, you would just try to find the smallest absolute difference, which you need this to be in sorted order because we're going to be using binary search. So let me show you how I tried and did it. So this is what this is. And then when you're at 3, the only option you have is 4. Again, you still don't have a left side because 1 minus 2 is less than or equal to 0. We're out of bounds to the left of the array. When you're at 2, then you have this is the only option because 0, 1, 2 plus 2 is 4. 4 is out of bounds to the right of the array, so there is no right side. Let's do this to make it more clear. And then when you're at 4, you have options 4 and 3. And you're at 4 again, nothing on the right side, so pretty simple. But this needs to be in sorted order for us to do the binary search to find between each of these what is the smallest with the current element, not between each other because each other is not at least x distance apart. So if you know that, let's go ahead and say low is going to be I minus x to find if there's a left side. High is I plus x to find if there's a right side to the current element. And then if low is bigger than or equal to 0, then we have a left side. And we can say before is going to be nums of everything up to not including low. And we want to sort it so we can run a binary search. But first, let's just make it simple. And if high is less than length of nums, vice versa, same thing. After is going to be nums of high to the end. And then for b and before, result equals to min of results of absolute value of the current element, which is nums of I, right? Which is going to be 4, 3, 2, 4. b minus nums of I. Same with a and after if there is a right side. Absolute value of a minus nums of I. And then at the end, you can return result. This is still going to be too slow, but we're still making progress. And I'll show you why. This is n, so this is basically like n squared. So it's just as bad as before, probably even worse. Again, time limit exceeded. So what we're going to do is make sure this is sorted so that we can run a binary search on it, right? So we're going to look for the left side, which is going to be bisect left inside of before, and we're looking for the closest element to current. And then we're going to ask if left is bigger than or equal to 0 and left is less than length of before. Yes, then we're going to say, because binary search basically, if we have 1, 2, 3, 4, 5, and the current is 4, then we're going to land on this index, but the closest might be 1 to the left or 1 to the right, or the current element at the same place. So let's just make sure. And so result equals min of result and absolute value of current minus, what is it? Nums of left, right? If left minus 1 is bigger than or equal to 0, then result is min of result. That's 1 to the left. We're checking 1 to the right just to make sure there are no edge cases. Cur minus nums of left minus 1. If left plus 1 is less than length of results or length of before, then result absolute cur minus nums of left plus 1. Right. So, and then we can do this for after as well. So right equals bisect left inside of after current right, and this is still too slow, but I'm just showing you the thought process here. Right and right. Okay, if it's just out of after, length of after, not before. So after sorry, this is supposed to be after of right because not nums. It's supposed to be before of left. Before, because we already isolated that specific sublist that we're going to do the binary search on, right? So this technically works, but again, it is still too slow. And the problem is this is still n when we sort it and then slice off a part of the entire list. So the way we're going to take care of this is with the sorted list. So we're going to intelligently call this before is sorted list and after is sorted list. And the main efficiency comes from the fact that we're going to first add everything from 0 plus x to the end, and then we're going to slowly remove, chip away one by one because we're here, then x is everything from here to the end. And then here, we're not going to have anything, but we're also going to add something from before, and we're going to do this one at a time. So nums of x to the end. And if low is bigger than or equal to 0, then that means there is a left part, right? So instead of this, we can say before.add nums of low, right? So when we're here, we finally have a left side, which is 4. And then after, if high is less than length of nums, then we're going to slowly remove the first element to the right from I plus x, right? So after dot remove nums of high. So just to illustrate what this means is, for example, a sorted list first starts like this on the left, and then on the right it's going to be 2 and 4, right? So on the first iteration we're on 4. That's fine. On the second iteration we're on 3. What we're going to do is there's still no left side, but the right side is going to become just 4 because we removed this 2, because from this position the 2 is not at least 2 blocks away, only 4 is. So that's why the right side is like this. When we get to this 2, then we finally have a left side. So we're going to add this to the left side. It's going to stay in sorted order because of the sorted list. And then the right side is going to be removed because there is no right 4 that's bigger. There's nothing to the right side that is at least x away in terms of indices to the right. And then what that allows us to do is not have to create another sorted list every single time, which is n itself. And that will hopefully is what I did. There you go. So gets over, time limit exceeded, and took a lot of work, pretty low acceptance rate. So I'm really happy that I solved this on my own, but it really just takes a lot of tinkering, and hopefully this kind of made sense. And thank you for watching, and stay tuned for more.